In the field of X-ray fluorescence, XRF, process analyzers, the main applications are ore and charge analysis, as well as pulp analysis. These are either bulk solids or liquid process products. Typically, there are manufacturers who specialize either in XRF analyzers that analyze ore.
Either there is some change in the elemental composition, or we demonstrate accuracy with a probability of 75%.
The cost of a single analyzer with 8 to 10 control points was equal to the cost of 8 to 10 of our analyzers. And so we clearly see that 10 analyzers are definitely better than just one.
By offering a comprehensive solution and providing a solution that is valuable to the shareholder, this task is accomplished, just like many others we've discussed today.
I'd like to thoroughly break down our complex topic a little bit more in terms of these important on-stream analyzers. The main directions: there are two areas in on-stream X-ray fluorescence analyzers. These are ore and charge analysis and pulp analysis. So we're dealing with either bulk solids or liquid process products, right? And as a rule, there are manufacturers who specialize either in XRF analyzers for ore analysis or analyzers for pulp. From this perspective, we have a unique experience in that we produce essentially a universal instrument that works in both areas. And there have been cases where we install and equip the entire plant turnkey. That is, it is a unified spare parts inventory, which again, from an operational efficiency standpoint, reduces overhead costs for operation. It is a unified metrological and software solution, which again optimizes maintenance. After all, it's easier for a specialist to work with a single software program than with a large, diverse array of heterogeneous equipment. Now, I would actually like to dive a bit deeper into this fascinating subject, since I know you also possess extensive experience and a profound understanding when it comes to highly precise ore feed analyzers. Let's therefore talk a bit more comprehensively about the specific characteristics and operational nuances of this particular type of essential equipment, exploring its key features, intricate nuances, and what discerning customers should meticulously pay close attention to when carefully choosing and ultimately selecting such critically important equipment for their specific operational needs. What I would like to share is specifically in the context of the three main types of equipment to give customers some guidance, essentially a direction, on which types of analyzers are preferable for different tasks related to ore feed. This is based on the methodological features of this equipment. That's why it's a very relevant task for us to really understand what exactly is coming from the open pit or from the underground mine, what kind of ore we are actually receiving, whether it's rich or poor. The market leaders, the very large companies, have gone even further and started addressing mineralogy issues. In other words, it's not enough to just know the material composition. Now it's necessary to move further and understand things at the mineral level. Such tasks are also being set. There are indeed significant and important nuances when utilizing this specialized equipment, particularly such as when we are dealing with raw ore that contains rather large and substantial chunks, sometimes measuring up to an impressive 40 centimeters in diameter. There are, in fact, a great many subtleties and intricate details involved in accurately measuring this ore in its initial unprocessed state, right after it has been carefully extracted from the ground and following some primary crushing processes, where the individual pieces are typically about 30 centimeters in size. Based on your valuable professional experience, what are the specific and intricate nuances that one should carefully consider when utilizing on-stream analyzers, especially when these instruments are applied to analyze ore that contains particularly large and irregularly shaped chunks of material?
Yes, thank you for the question, Arseny Vladimirovich. Indeed, this particular nuance is quite profoundly significant, and it inherently makes its own crucial adjustments to the fundamental concept of geometallurgy, primarily because geometallurgy is precisely the scientific discipline that comprehensively allows you to meticulously configure the entire processing flow in such a precise and optimized way that the overall extraction efficiency consistently remains well within clearly foreseeable and readily understandable operational limits. Because the losses that occur during flotation, and not only during flotation, but all the losses that arise from the entry point to the output of the finished product, this is exactly the area that needs to be addressed. In order for an enterprise to understand what it is extracting, typically some kind of cloud model is built. That is, we understand that we cannot extract everything at once. We understand that the ore body is distributed in a certain way, Somewhere it's poorer, somewhere it's richer, but on average, as they say, it's 37.7 across the board. This is not always a convenient position. However, for the technological process, this is very important. Therefore, as we move along this cloud model, we are faced with the task of verification. Are we moving correctly within this cloud model? Because one thing is drawn in a certain program, and the way things like subsidence are formed in order to understand where our drilling and blasting operations are deviating, whether they are following the planned vector correctly, is another. We need to take a look at that. There, geological exploration is involved. We understand some figures, large chunks have been extracted and brought to the surface. The question arises, did we extract the right amount? And is it correct to compare the geological exploration data with what is actually being sent to the plant? Why? In order to, let's say, use the simplest solution, an enormous ore yard where sorting is done by piles, specifically according to their elemental composition, so that roughly speaking, one pile doesn't have 1% and another 5%. We need to have 3.5% everywhere. This can be done on the surface. And this nuance, yes, it is indeed a problem. When large chunks of material are moving along the conveyor belt, for example, how many truly effective ways do we have to accurately determine what's on the conveyor? One practical and reliable way is to take a representative sample and subsequently send it to the lab, put it into the MLA to thoroughly see what values are actually there. The second option is to use an on-stream analyzer, which, well, we need to mention here how effectively it can tell us and how well it can be calibrated within the range that interests us. And so that we can say, yes, this calibration tells us either that there is a change in elemental composition, what kind of change it is, or we can show accuracy with a probability of 75%. This particular problem, well, I honestly don't really know. It seems that almost everyone in the industry has encountered it. It's abundantly clear that the vast majority of manufacturers operating today confidently claim that they possess the capability to accurately show precisely what is present on the conveyor belt. Some of them assert this with a 30% probability of success, while others state a mere 10%. But crucially, no one definitively says that their solution is sufficiently accurate enough to meet demanding industrial standards.
It's a very interesting task, yes. On the one hand, it's not simple. There's a lot of methodological and scientific background to it. If we start digging into that now, we probably won't have enough time. It's a topic for another conversation.
I think that should be in a separate section somewhere, or we should just make separate podcasts about it.
The problem is that there are large chunks of ore and the RFA analyzer only samples a shallow depth. The neutron analyzer scans through the entire layer. From this perspective, the client is always weighing two sides. It seems like scanning the whole volume should be more accurate. And there's always the ongoing challenge of choosing between the IRFA or the neutron analyzer. And the client inevitably always has doubts about the RFA analyzer, but these can generally be successfully addressed and methodically demonstrated with mathematics, showing that this method, this type of equipment, also has its place, and in terms of accuracy, may be no worse than the neutron analyzer. Now, another point, you've noticed that there are two ways to measure: the laboratory method, where you take a sample from the conveyor belt. But that's not a trivial task either. When you have a conveyor belt moving at high speed with large chunks, boulders, really about 40 in size, and honestly, in practice, the task of sampling becomes, let's say, virtually impossible. That is, to take a sample.
I agree.
When the belt is moving, in practice, it really becomes impossible, so to speak. And from this arises another problem for us. Let's say we can install something, but we can't directly verify it. For example, there's some analyzer installed, material passes under it, say 10 or 20 meters of it. It gives some measurement. We take that material, reduce it, grind it, go to the lab, get some number, and then just compare the two numbers head to head. It doesn't work like that here. You can't do it that way in practice. That's the whole difficulty. Well, I'm not talking here about using a laser analyzer. You can immediately rule that out, since it targets a specific point, while we have a lot of uncertainty with larger chunks of ore. But I wanted to highlight this nuance. Over the years, the client compares two solutions, these two physical methods of analysis. And here, among other things, our company is tasked with developing methodologies and solutions that, from the perspective of using an XRF analyzer, can finally clarify this issue. Probably an easier task to solve is the analysis of the charge or already processed ore. These are not such large pieces of ore where there is some possibility to do preliminary preparation.
If I may, an important remark needs to be made here, a very serious one. Well, look, this approach of geomethodology actually provides an answer to this question. When we measure the charge, for example, after the mill, yes, the ground material, it's essentially the same issue as when we measure the tailings. This is the final part, which is already unclear how to influence. And if a company is seriously considering improving its overall operational efficiency in terms of eliminating technological losses, then the crucial work of this particular section, specifically the mining block and the delivery block up to the plant entrance, becomes very important and highly relevant. This is because you can effectively try to solve the problem head-on, for instance, by meticulously scanning the entire chunk with a sophisticated neutron analyzer, say a substantial 60 by a meter, or perhaps 60 by 60, or even 30 by 30, for example. But in the end, this particular approach doesn't actually solve the fundamental problem of precisely how the plant should be properly and effectively fed, so to speak, in order to truly start eliminating technological losses right from the very initial point of feeding, which is a crucial aspect to consider. After all, if we effectively manage the feed and significantly reduce the variability at the plant's input, we can confidently say that the overall stability of our flotation process will be remarkably different. Indeed, it will be distinctly different and considerably more appealing to the discerning shareholder. Therefore, perhaps from a purely scientific standpoint, we absolutely shouldn't try to forcefully break this particular stone with the ultimate goal of knowing absolutely everything about it. Maybe, just maybe, it would be considerably better to carefully look at, or indeed, to thoughtfully guide various enterprises toward their optimal point of maturity, so that they can fully understand, yes, it is undeniably difficult, and yes, it truly and genuinely pushes them far out of their established comfort zone. Yes, it's quite a construction, such an ore yard, where all this is mixed in winter, summer, autumn, with snow and everything else. Yes, it's a serious task to verify what happened at the geological exploration stage, to confirm and adjust the correctness of extraction, the correctness of bringing the ore to the surface. These are big questions, and I don't know how correct it is to set the task like this. Let's just install one device that will allow us to measure anything we want at the entrance. You could do that, but is it really the right approach?
So, if I understand correctly, measuring alone isn't enough. You need to make some management decisions. Technical
and management decisions. Exactly right.
Here, Vyacheslav, I remembered a very important nuance that probably comes up from a metrological point of view. When we install some equipment and take measurements, what you mentioned, to verify, to understand whether it's correct or not. This is exactly where the stumbling block lies. Specialists always have doubts about the margin of error, the reliability, and how much we can trust the data we see, the numbers we measure, and so on. It's a complicated issue. A lot of debate has taken place here. This often happens precisely because it is indeed very difficult to verify, but what I would like to draw particular attention to here when we talk about the crucial metrological aspect is that there is a certain inherent bias even when we manage to take a control sample after the analyzer. The analyzer meticulously measures for a period of 5 minutes, and during those 5 minutes we methodically collect some material and then proceed to make a thorough comparison. Overall, it's generally assumed that chemical analysis in the laboratory is the absolute truth, and when you subtract the chemical analysis data from the analyzer readings, the entire difference, the error, is attributed to the analyzer. Probably for our audience who will be watching, I'd like to add a remark. Every laboratory, every chemical analysis has its own permissible margin of error, operates within a certain error range, and there's also the error from sample preparation, which doesn't just disappear. These errors don't simply add up directly, but are combined according to certain mathematical formulas. There's also the representativeness of the analysis to consider. So we come to understand that there is some overall cumulative error, which is determined by the sum of several errors, from the process analyzer, the laboratory, the representativeness of the analysis, and the sample preparation. But the absolutely key and crucial question, and here I completely agree with you on this point, is what precise margin of error is truly acceptable for us in order to effectively achieve the desired and intended effect, the ultimately desired and successful result? And what is that result? Yes, what exactly is it? So often what we end up with is a dialogue and a struggle for accuracy. But there's a lack of understanding at a higher level as to why we are striving for this accuracy. What are we fighting for? In other words, what is this accuracy actually for? What will this accuracy give us at a higher level? Maybe we don't need ultra precision down to hundredths of a percent. Maybe some probabilistic level is enough for us, right? This really is a very important question. To rise a bit above and determine methodologically what level of accuracy is actually sufficient and necessary for us to achieve the effect and result we want, and whether it's worth fighting for and pursuing that level of precision. And it's clear that any problem can be solved. It's just a matter of effort, money, and time, again, right? And when we talk about accuracy, it's always, well, let's say a financial issue, a matter of resources, a matter of time. And here, it's absolutely necessary to link this to operational efficiency. What level of accuracy is necessary and sufficient for us to solve the given task? And this connection, of course, often gets overlooked, or it simply doesn't get any attention. But what I often see is that there isn't a higher level understanding or research, some kind of information about what level of accuracy would be sufficient for us, a justification for why that accuracy is enough, whether we need higher accuracy or if the current accuracy is sufficient, or even, roughly speaking, whether we just need some kind of indicator to understand whether we're moving up or down. So,
Look, before I get too far ahead of myself from my extensive experience, the raw material typically comes into the processing plant, and then, subsequently, it gets thoroughly crushed and broken down into smaller pieces. You ask people, what are your losses at the crushing stage? And people can't answer that question. Why can't they answer? So what's the starting point here? How many percent of waste rock should there be in the incoming raw material? Is that considered a loss or not? Let's say the mill operates for about 28 minutes per unit volume to grind the ore to the required stage so it can go to flotation. Is there any loss here? Again, people can't answer. But if you really look into it, the losses during those 28 minutes, this figure is specified in the technological regulations, we understand that if it's waste rock, the grinding happens faster. We will either overgrind or undergrind. If we overgrind, there will be nothing left to float. That means there will be massive losses in the tailings. How can you influence that? This is a simple case, which of course becomes obvious during a deep diagnosis. When you lay everything out on paper and give it to the person responsible for the plant's results, or let the shareholder read it, they naturally start asking all the same questions. Where are the losses here? What is their magnitude and how do you plan to address them?
yes, thank you very much for that insightful remark. This is indeed a particularly illustrative and highly relevant case. As for the detailed analysis of the lenti converter charge, the task here is not exceptionally difficult or overly complex. The material is already thoroughly ground, significantly more heterogeneous, and considerably more uniform in its composition. At this stage, it's already possible to make various engineering decisions and so on. Among other things, we have a patent that combines 3 different solutions: hardware, engineering, and methodological solutions altogether, which we are currently patenting in 18 countries around the world. We are grateful to them for this. They are providing support in this regard. After all, the golden ratio of the original fluorescent equipment is that one of its broadest applications is for liquid technological products, primarily pulp, to a lesser extent solutions, and even less so, perhaps, suspensions, for similar repairs. This is a very interesting topic for discussion about pulp analyzers, and we probably won't be able to give our listeners a definitive, exhaustive answer, but rather leave it as an open question for discussion. Think about it, we'll lay out the pros and cons. We are probably the company that goes against the generally accepted approach when it comes to sample delivery systems, to delivering samples at the plant. These are usually lines that stretch for tens or even hundreds of meters. And at a certain point, some plants were designed a long time ago, They're just elongated, and in such cases, it's simply impossible to implement this kind of sample collection and delivery system because the plant is too stretched out, the routes would be too long, and it would be very difficult to transport samples over such large distances. Some people, simply out of frustration with operating these sample delivery systems, decided to place the analyzer directly at the control point to eliminate this complicated process. Delivering and transporting the sample directly to a single analysis point at the plant is a labor-intensive and complex process to implement, since the plants are large and the routes end up being very long. The advantage of our analyzers is that we can install them directly at the analysis point, which means very short pipelines, bypasses of just 2 to 3 meters, that almost never get clogged, maybe only once a year. But even then, it's not a big deal. A 2 to 3 meter pipe can be easily replaced, it doesn't cost much, you don't even need to clean it, you can just put in a new pipe and so on. But again, let me repeat. Based on our operational experience, the likelihood of it getting clogged is practically minimal because it's short and everything is simple. The longer the pipe, the higher the chance that it will get clogged with sludge. Here, there's a question that can be quite tricky, maybe even a bit challenging, one that we're searching for an answer to but can't seem to find. When I talk to technologists at factories or with other people, there's a particular point I'd like to highlight in this industry. And how is the question posed? So, for example, there's a classic solution where, well, it just so happened that the level of technology, engineering, and electronics wasn't advanced enough to produce a device, an analyzer, that could be installed directly at the control point on the pipe, like a density meter. When all this was developing in the 1950s and 60s, there was no such possibility, so it was decided to place the analyzer in a separate room, and we would pump the pulp from the plant. But then, what started to happen next? Technologies began to develop, and in principle, it became possible for us to produce a device that could be installed directly at the control point. Moreover, the cost of the market leader was such that the price of one analyzer for 8 to 10 control points was equal to the cost of 8 to 10 of our analyzers. In other words, and we end up with a situation where 10 analyzers are better than one. Well, probably from the point of view that if they cost the same, even in terms of fault tolerance, if one breaks down, the other 9 keep working. Objectively, that's better. It seems like all the colleagues I talk to and present these arguments to agree that it's better. Next, we install it directly at the control point. We need a space of about 2 by 1.5 meters to set it up, and the installation takes about 1 to 2 weeks to deploy the analyzer at the site. That's it. From this perspective, it would also seem better. There's less chance of things getting jammed up in terms of operation and maintenance. So, if we talk about the paradigm, we're still in that same paradigm. There are solutions, there are facts, there are already implementations, and in some places they've even been working for decades, but everything still keeps moving along the same old tracks. Well, as the joke goes, nobody ever got fired for buying Oracle, right? But from your point of view, how can we overcome these paradigms when it's just more comfortable, easier, and probably more reliable to keep going down the old tracks than to experiment with something new? Although it would genuinely seem to be the case that when I directly ask experienced technologists or individuals with significant practical experience in the field, I don't really encounter any particularly strong, compelling reasons or substantial counterarguments that would explain this phenomenon. So, this naturally leads to the question, why exactly does this situation happen? Why do these innovative new technologies consistently have such an incredibly hard time successfully entering and being adopted by the established industry?
You see, the comfort zone is such a wonderful thing where a person understands, especially if they're approaching retirement age, even though that's been raised a bit now, the meaning is very simple. I've worked like this for 10, 20, 30 years. And I'll keep working this way, and I won't have to do anything differently. There is no need to change anything at all, just keep going exactly as before. Yes, there are some inevitable losses, But so what does that truly matter? The shareholder will pay for them. I'll still have my job right here, and I am perfectly fine with that. Therefore, when it comes to the number of analyzers at the designated point, this information, I'll repeat once again, must be valuable to the customer, and it should be presented to them in such a way that they can see their own profit and the increase in efficiency that they are aiming for. In order for things like this to happen, you still need to follow a win-win approach. Everyone involved in the process should receive their medals and rewards, and we, or in this case you, should get that point in your reference stating that thanks to the implementation of the analyzers, it was possible to solve tasks A, B, C, D, E, F, G, H, I. When all of this starts moving forward and is declared by the shareholder, then no one will care about that comfort zone or the easy path that someone might take for the rest of their career as a technologist, director, or factory manager. It will no longer matter at that point. That's why, by selling a comprehensive solution and providing a solution that is valuable to the shareholder, this task is accomplished, just like many others we've discussed today.
Yes, thank you, Vyacheslav, for your comment. That's a very interesting point. Nevertheless, there are many tasks that we are now able to solve with this approach, primarily for our solution. I wonder, what about factories that haven't yet operated equipment of this type?
Even those that have operated it, still, if we use the right approach, where we explain why there's no need to circulate pulp around the factory and why it's easier to reach the target number. Again, it seems obvious. But is it valuable for the customer? Is it valuable for the client? And if it is valuable, then why?
Yes, that's an open question. I'll probably repeat myself here. As I said at the beginning, we probably won't provide any exhaustive solution, but rather leave this question hanging in the air. Modern means of communication also allow people to share their opinions, express their wishes, and offer their critical reasoning, so to speak, their thoughts and objections, so let's leave room for that as well. It's a rather complex and ambiguous question. From the perspective of communicating with a number of people responsible for the technological process, they have a clear frame of reference. In the 21st century, a factory should be transmitting digital signals, not just pumping pulp around. There is also an opposing point of view, including counter-arguments, that this is essentially a framework, an established scheme for organizing a factory, where pulp is delivered to a single room where, in principle, a composite sample is collected. Some enterprises, let's say, may also reject such solutions. So, in the end, everything is highly individual. It's a matter of personal preference. Nevertheless, one of the reasons why it was decided for the purposes of this interview again is to highlight that at the very least, such an option does exist. Because, as practice shows, even though we have been on the market for a long time, not all enterprises know that this is actually possible, that such an option exists. You can install it directly at the analysis point. This makes it possible, so to speak, to deploy the analyzer very quickly at another facility, and with your own resources move it to a different location in 2 or 3 days. If, let's say, the technological issues that needed to be monitored at the current point have been resolved, you can move it to another section and set up the equipment very quickly. This is probably our competitive advantage, and it's what we wanted to convey to our target audience, dear viewers who are watching this video.
Well, all these questions are actually addressed by the pre-project survey, which ultimately tells us that probably there's no need to digitize absolutely everything. Perhaps in some section of the workshop, yes, it might actually make sense to deliver a sample manually, and that would be perfectly fine. And in some places, you definitely need to work with digital data. So, when you come to the facility and work through the issue together with your colleagues, you need to make a custom decision that specifies how many points will be digital and how many points will involve delivering pulp samples to a certain location. This is a completely normal practice.
Yes, I suppose our position is this. We're not trying to start some kind of revolution. Rather, we're trying to highlight that there is also the possibility to supplement the existing system and install an analyzer at the control point. Again, I want to emphasize that we pay a lot of attention to the methodological aspect of measurement accuracy. So when it comes to results, we provide reports that clearly show and track the accuracy of the analyzer, the repeatability of measurement results, so that the customer has no blind spots regarding the performance of our equipment.
Arseny Vladimirovich, well, it seems to me that you're talking about the middle part, about making the analyzer show accurate results. But to begin with, as I see it, you first need to take a sample from today's range. You need to carry out certain work to calibrate the device. As a result of this work, it is necessary to exclude those samples that clearly do not fit into the framework of the mathematical model by which the exact values will be determined. If the client doesn't do this, if we fail to provide them with certain competencies in this area, they probably won't be able to do it, and the reports won't help them either. What do you think?
The report is built on this data. Without this data, there will be no report. Of course, if we move on to the methodological aspect, but it's probably, well, if we're not talking about chunks of ore that are 30 centimeters big, in principle, it's a fairly manageable task to take control samples after the analyzer to do some kind of control sampling. Just directly compare what the laboratory shows and what the analyzer shows, right? It's quite a doable task as long as we're not talking about heavy-duty conveyors. And our experience shows that we've come to the conclusion that we need to offer ready-made solutions so that the client has no questions left in this regard. And of course, we make sure that control sampling is carried out, because otherwise the results of the element content measurements start to be interpreted, let's say, subjectively, right? There's no confidence or reference points. Can we trust these results? And what did we actually get? Without this kind of thorough analytical work, whenever there are doubts, we have an argument in the form of a report to address those doubts. Well, dear client, here you go. We took the samples, measured them, and here is the margin of error, whether it's within the limits or not, right? We try to dot all the I's to put this question to rest. Otherwise, again, returning to the issue of operational efficiency and probably to broader questions of operational management. As I understand it, things move forward without solid ground under our feet, without certainty that these are truly reliable figures to operate with. Our entire plant, so to speak, pyramid, and all our intended solutions collapse. If we can't rely on this data to actually manage the process, then without that solid foundation, everything falls apart. That's precisely why we initially encountered this particular issue from the very beginning, a considerable amount of time ago, and we have diligently worked through it methodically and systematically. Now it's a truly streamlined and efficient process. And the purpose of this is to ensure that there are no doubts at the enterprise regarding the reliability and accuracy. Of course, this does require some effort from the company, as well as some minimal financial investment. But without this, I believe you'll simply end up with an expensive toy, an expensive piece of hardware, and you won't have the confidence or understanding that you've actually purchased a metrological instrument you can trust. And Vyacheslav, I would like to sum up our conversation today. I'd like to conclude with my own perspective, perhaps with some recommendations for companies that are choosing a tool. I'd like to hear your recommendations on how to use this tool within the operational efficiency chain. How should one approach the issue of operational efficiency and view this tool in the context of operational efficiency? Briefly, if possible.
Yes, of course I can. I believe that a company should follow the right path. This path must necessarily include close collaboration between tech and analyte instrument specialists and those involved in operational efficiency projects, so that they can review the developments and cases they have, especially those that have not been implemented, perhaps because they don't know, don't understand, don't see, or simply lack the necessary competencies. In this case, issues related to survey forms, their proper completion, and the opportunity to delve into technological regulations will be resolved, allowing us to determine what truly deserves attention, taking into account new technologies, new reagents, and everything else that can help. And at the same time, we can meticulously record the comprehensive economic effect, both the potential and the actual impact, so that we can effectively present to our valued shareholders with information that is truly valuable and highly relevant to them, making it abundantly clear exactly what precise amount of cash is being generated and how it significantly impacts the overall free cash flow of the business.
Thank you. Thank you for your answer. For my part, I would like to summarize regarding the selection of analytical equipment, including process analyzers, and highlight what aspects should be paid attention to. First of all, pay attention to the company's specialization, because as we know, the broader the focus, the less sharp the results. Consider what competencies and background they have in this field. And secondly, of course, an obvious and rather basic thing is references and what experience they have in these matters. And thirdly, I would probably like to add, more as a suggestion for clients, not to be afraid to experiment, to look towards innovation and new developments. Unfortunately, not all enterprises do this, but most have launched programs for transformation and business processes. I have to say, these programs work and people pay attention to new developments and innovations, latch onto them, and this is very encouraging for companies like ours, whose main focus is, of course, on R&D, research, and solving complex, unconventional problems. Thank you.
Thank you.
Dear esteemed viewers, if you still have any lingering questions, if you possess any valuable suggestions, or if Vyacheslav Mikhailovich and I perhaps didn't fully and comprehensively cover a particular topic that is also highly relevant or could be of significant interest to you, please feel absolutely free to write to us. And do leave your thoughtful comments. We will most certainly and diligently try to get back to you with constructive feedback, to answer your specific questions, to provide detailed and thorough responses, or maybe even to record a brand new and engaging discussion addressing the truly pressing and highly relevant issues that various enterprises are currently facing in today's dynamic world.
Yes, I suppose so. If you find any inaccuracies in our speeches, it doesn't mean that we lack competence. You can consider it as food for thought, as a reason to continue the dialogue.
Yes, perhaps that's an important remark. We are not claiming to have the ultimate truth. Our approach is more of an open dialogue, reflections on the topic, so that we can bring pressing questions into an open discussion with industry specialists and factories. This is also the message from our company, not to engage in picketing or pressuring customers, but to try to follow an effective and constructive path. Therefore, everyone is welcome to join the discussion, to participate, to get involved in the workflow, and to contribute to productive and effective work at enterprises aimed at improving methods and equipment for analytical control. Thank you.
Thank you.